So good morning, everybody. I welcome you to the last but one section. And the first speaker of this section is Richard Garner, and his talk is about the variety of Cartesian closed varieties. So please, Richard.
Thank you very much. And it's a pleasure to be speaking to you all from rainy Sydney. So what's this talk about? Well, it's about varieties which are Cartesian closed. So what's a variety? I'm going to mean by a variety just the category of algebras for some finitary monad T on the category of sets. And of course, like any category, you can ask, when is that category Cartesian closed? And that's a question which seems to have gone unanswered for a surprisingly long time. But Peter gave a complete answer to that question in the 90s in a paper called Collapsed Toposes and Cartesian Closed Varieties. So among other things, Peter in this paper gives a complete kind of syntactic characterization of those varieties which are Cartesian closed. So today, what I'm going to tell you is I'm going to give a reformulation of Peter's result, which is a little bit neater, and which in particular tells us that Cartesian closed varieties themselves form a variety, which thankfully is not itself Cartesian closed, otherwise we'd be in terrible trouble. All right. So let's think about some Cartesian closed varieties that we might be aware of. So these are sort of the simple and basic cases. So one that we're quite familiar with is M sets. M sets is just the category of sets with an action, in this case, a left action by some monoid M. And that is, of course, a pre-sheaf category, so in particular a topos, and therefore Cartesian closed. And all right, so we can see on the left here what an action of a monoid on a set looks like. And what's the internal Hom? Well, it's just the usual pre-sheaf Hom. So the internal Hom from X to Y, if these are M sets, is just a set of M set maps from X times M into Y. And in order to make that into an M set itself, well, I kind of just take this M here and I act on it on the wrong side inside here. Okay. All right. So here's one that's maybe a little bit less familiar. So this is due to George Bergman in 1991. And so he didn't talk about this being a Cartesian closed variety, but he came up with this notion of B set. So if you've got a Bullion algebra B, then I can talk about an action of B on a set X. And so what is this? Well, for every element little b of my Bullion algebra, I have basically a binary operation from X times X into X. And I write that as B XY goes to B brackets XY. Okay. So if you're a computer scientist, you might think this is sort of if B, then X, else Y. And there are two axioms that has to satisfy here. If you were a category theorist, you might also think of this in this way here. So B set, well, I can look at a sheaf on this Bullion algebra B. And I can look at a Flask sheaf. So Flask means that all the reindexing maps are epimorphisms. But in the case of a Bullion algebra, this is really simple. It just means that it's either empty or it has at least one global section. Okay? So that's what these B sets are. And the idea is that this X is the set of global sections. And this operation that we have here takes two global sections, X and Y, restricts X to B and Y to the complement of B, and then glues those together because that's a nice cloak and cover. Okay. And so what's the internal Hom? Well, this turns out to be a commutative variety. So the internal Hom is just the usual Hom for a commutative variety, which in this case turns out to be actually part of a Cartesian closed structure. Okay, so it's just given pointwise. Okay. So these particular classes of Cartesian closed varieties, we can characterize them in various ways. So I guess I'll start with M sets, which is probably a bit more familiar to you. So given a finitary monad T on the category of sets, then it's the M set monad precisely when, so we can just give a characterization in terms of the monad itself. We can say it preserves all co-limits, or equivalently the forgetful functor from the category of algebras down to set creates all colimits. I guess it's another way we could say it. And we can also characterize it syntactically in terms of the theory T by saying it's generated by its unary operations. Okay. All right. So how about B sets? Well, the following are equivalent if I've got a finite tree monad on set. It's a B set monad for some B. Equivalently, it preserves finite products. And so there's going to be these various hedging clauses here. So I'm going to say it's not the terminal monad here. And maybe I can say a few words about that in a second. But basically, I just want to say that it preserves finite products for now. And then the third condition is that it's commutative and it's generated by hyperaffine operations. So I mentioned commutative already, but let me just write that down in case you're not familiar with it. Commutative means all the operations commute with each other. And what does all the operations commute with each other mean? So here's two operations of my theory or finite tree monad T, F and G. And so it says if I take F, and then so I'm going to list the arguments of F by using some lambda notation. So I'm going to say the ith argument of F is the function G, the operation G applied to the set of terms whose jth argument is xij. And on the right-hand side here, I have the same thing, but with G and F interposed. Okay? And basically what that says is that if it's a commutative theory, then each operation F from x to the n to x is in fact a T algebra homomorphism. Okay? And that gives you a canonical monoidal closed structure on the category of algebras. And in fact, this hyperaffine business is what forces that monoidal closed structure to be Cartesian closed. Okay, so basically it tells you that this canonical monoidal structure on the category of algebras for any commutative theory. And maybe I should say what that monoidal structure is. Its internal hom is just given by the pointwise hom. So exactly this formula here that we saw before. So basically, if I've got two T algebras, I take all the T algebra homomorphisms between them, and that itself forms a T algebra due to this commutativity. So that's the internal hom, and there's the associated monoidal product. And in fact, hyperaffine is what forces that monoidal product to be Cartesian product. And so what does hyperaffine say? So hyperaffine, an operation F is called hyperaffine if, so this is affine, right? I mean, okay, that is affine. And then hyperaffine, so it just says if I set all the arguments the same, I just get back the argument I put in. And this one here says if I take F and I apply it to the thing whose ith argument is F applied to the thing whose jth argument is xij, then that's the same as, when I write this correctly, which I seem not to have done. So that's the same as applying F to the family whose ith argument is xii. So I take a sort of diagonal like that, and that's called hyperaffine. All right. So, as I mentioned, Peter has a result which characterizes the Cartesian closed varieties, and I've written it out in its full bloody detail here. So I'm just going to talk you through this. So to start with, we have a little definition. So I've got a finite tree monad T. I've got a term, an n-ary term Q, and I've got one of the indices of from 1 up to n. Okay, and then I'm going to define for any two terms T and U in the same free variables, I'm going to say that T and U are equal in the ith place of Q, which I write like this, if T and U are equal in the ith place of Q. So what does that mean? It means that if I take Q, I feed it some variable arguments here, except in the ith place where I either stick T applied to a disjoint set of variables Y or U applied to a disjoint set of variables Y, and I require that these two terms here are the same in the theory T. Okay? All right, and so here's Peter's theorem. So let T, so again, I'm going to hedge around with T is not the terminal monad here, be a finite tree monad on set. Then T alg is Cartesian closed if and only if, and then we have two conditions here. I'm just going to read through these, and I'm not going to make any attempt to say anything more about them, except to note that they're maybe slightly more complicated than one might like. Okay, so for all P in Tn, there exists Q in Tm, and families UV of unary operations, M unary operations, and a function alpha from M to N, these finite sets, such that if I take Q and apply it to lambda I applied to UI of X, and that's equal to X, and UI substituted with P inside it is equal in the ith place of Q to VI applied to X alpha I. Okay, all right. So having done that, maybe I don't have the energy to read out the second one, but I guess the point is that although these conditions might seem a bit ad hoc, they're actually incredibly useful in practice. So if you actually want to check if a monad or a variety is Cartesian closed, it's not very hard to check these conditions. And so in fact, Pattinson and Schroeder kind of essentially rediscovered these conditions some time later and used them. I mean, they were doing things about kind of completeness of co-models or something like this, but they kind of basically rediscovered these conditions because they were really useful for proving some kind of completeness result. Okay. All right. So here's my reformulation of Peter's theorem, and I should emphasize that this theorem starts from Peter's theorem. So without Peter's theorem, I wouldn't have this theorem. And what does it say? It says let T be a non-terminal finitary monad on set. Then TL is Cartesian closed if and only if each operation, each n-ary operation, has a unique decomposition as follows. P of X is equal to H, a hyperaffine operation, applied to the set of terms whose ith entry is M applied to Xi, where M is some unary operation. Okay? So that, I think, is, I mean, it's certainly easier to write down and understand. And so how does it work? Well, basically, this, in Peter's characterization, gives you existence, and this gives you uniqueness. And the key step is that starting from Peter's results, so starting from a theory that satisfies these conditions here, we show that every affine operation is hyperaffine. So that's the first step in the proof. And I actually proved this, then forgot how I proved it. But I remembered this fact. And I was very pleased that after several days of forgetting how to prove it, I managed to use this fact to reconstruct everything else. So maybe you can as well. Okay, all right, so that's the theorem, but what can we do with it? So here we go. So if TL is Cartesian closed, then I can look at its unary operations, and that gives me a monoid, of course. On the other hand, I can look at all its hyperaffine operations. Now, we said before that if a theory is commutative and all its operations are hyperaffine or generated by hyperaffine operations, then it corresponds to a Bullion algebra. Now, in fact, from our theorem or Peter's theorem, whichever you please, you can show that the hyperaffines form a commutative subtheory. And so when I restrict to these hyperaffines, I get something which is a Bullion algebra. Okay, and I can say exactly what these are in terms of the original monad. The monoid is just the unary operations. And then, so then I look at the binary hyperaffine operations, and that tells me what the Bullion algebra is. Okay. Now, from our theorem, we know that B and M together determine T because of this decomposition here. So an obvious question to ask is, what are the extra structure and axioms that we need given a Bullion algebra B and a monoid M in order to reconstruct this monad T from it? Okay. Well, here's some structure that we have in this case. If I take a binary hyperaffine operation and two unary operations, then I can apply the binary to these two unaries, and I get a unary, and so that gives me a new element of my of M. Okay. On the other hand, I can take a B in this is B and an M in M, and I can substitute B into M, and I'm going to get a new binary operation. Now, that binary operation is not probably going to be hyperaffine anymore, but by our theorem, we know that it decomposes uniquely as something like this, where this is hyperaffine, and this is some unary, which if you think about it, has to be the same unary as we had before, namely M, like if I set this and this to be x, then this reduces to m of x. And so similarly, if I set this and this to be x, this has to reduce to m of x as well. Okay. All right. But the extra ingredient that we have is this c. And so let's give that a name. That's a hyperaffine operation derived from m and b. So let's call it m dot b. Okay. All right. And then we can write down what the axioms are that these data correspond to. So what have we got? We've got a Bullion algebra B, and we've got a monoid M. And then we've got these two bits of data here. And this looks very much like a B set action. And this looks very much like an M set action. And in fact, that's what we have. So I've got a Bullion algebra B and a monoid M, such that B is an M set, M is a B set. And then I've got some conditions here that basically say that certain maps are homomorphisms. So basically those two structures are nicely compatible with each other. And I'm going to call that a bicrossed pair because why not? But I should note that this was also introduced by Marcel Jackson and Tim Stokes in 2009 under the name B monoid. Okay. So obviously they start with a B and then say that a monoid M is a B monoid if it satisfies all this stuff here. All right, and so the theorem is, our first theorem, is that the category of non-trivial Cartesian closed varieties is equivalent to the category of these bicrossed pairs. Okay? Now, we can understand these bicrossed pairs in a kind of computational kind of way. So M, we think, is a monoid of total programs, and B is a Bullion algebra of tests. And so composition in this monoid is first do M and then do N, like this, okay? And then we can interpret these two actions. B, M, N is if the test B holds, then we do M, else we do N. And M dot B, so remember, this takes an element of the Bullion algebra and an element of the monoid and returns a new element of the Bullion algebra. And what we think is that what this produces is the weakest precondition such that B holds after executing M. Okay, so this is kind of a bit like Kleene algebra with tests. And this suggests, and in fact, I mean, this is also kind of, this is where Jackson and Stokes are coming from as well. But this suggests a different axiomatization in terms of partial programs. Okay, so I'm going to define P to be the set of pairs MB, which I think of as if B holds, then execute M, otherwise fail. Okay. And so the idea is that I identify two such things. So this is sort of a total thing representing a partial thing. And two total things will represent the same partial thing if they agree on the asserted domain of definition. Okay. So the domain of definition should be the same. And moreover, this condition here says that if I take M and replace the part of it that's not in B with N, then I get N. So that says that M and N agree on B. Okay, and in fact, this P has a completely algebraic structure. So what is that structure? I'll show you here. So a Bullion restriction monoid. So this is, so Robin Cockett and Ernie Manes have a paper on this, but also Jackson and Stokes have this notion under a different name. So it's a monoid P endowed with a constant bottom and a ternary operation like this, which we think of as if P converges, then Q else R, satisfying a heap of axioms here, which I'm not going to go through. But the point is there's not very many of those axioms. I think there might be 7. Yeah, there might be 7. And then, so the theorem is the category of non-trivial Cartesian closed varieties is equivalent to this variety of Bullion restriction monoids. All right, so I've just got time to sort of close the loop. So before we were able to give very explicit descriptions of what B sets and M sets look like, and what we can actually do now is give a complete description of what an arbitrary Cartesian closed variety looks like. So we know that it's always generated by a bicrossed pair BM, and I can define what I mean by an action of BM on a set. Well, it's a set X with an M action and a B action, and then some compatibility between those two conditions, between those two actions. And I can say, what's the internal HOM, showing that this thing is Cartesian closed? Well, I mean, this actually looks very much like the pre-sheaf internal HOM. And I mean, it does look like that, right? And then the actions are exactly as for B and M sets. So I'm just going to take 30 seconds to just talk very quickly through this right-hand part here, which is another presentation in terms of equivariant sheaves. So we said that these BM bicross pairs correspond to these Bullion restriction monoids, and these actually correspond under non-commutative stone duality to source-to-tile topological categories whose space of objects is a stone space. Okay, and we can express what these BM sets are in terms of this C, because I can take the equivariant sheaves on this topological category, and then I can take the two-valued collapse of this topos. So that means all the things which are either empty or have global support. And so Peter showed that this gives you a Cartesian closed variety, but now we have a very nice description of the topos which we collapse down to get this Cartesian closed variety here. All right, I seem to have run out of time, so I think I'll stop there. Thank you very much.
Thanks, Richard, for a very, very nice talk. Are there questions first in the audience? Let's see. One. Hi, Richard. Thanks for a really nice talk. I was wondering, on the side of the Cartesian closed varieties and this equivalence that you get, what are the morphisms? Are they?
Sorry, the morphisms in what? Sorry.
On the Cartesian closed variety side of the equivalence, is it morphisms of monads, or morphisms between categories of algebras? Are they Cartesian closed functions?
Right, right. No, it's just morphisms of monads, in fact.
Okay.
Yes, I mean, I think right, maps are monad morphisms. There we go. I even said it. I didn't manage to read that out, but it's written down there.
Other questions in the audience? How about the other question? Okay, go ahead.
Hello, Richard. Thanks for a very nice talk. I just wanted to say that, you know, I wish I'd thought of that myself. I was very nearly there when I wrote that paper. I knew that the unary operations and the hyperaffine operations controlled everything, but I just didn't think of looking at the way the two of them act on each other. And that is a wonderful description that you got there. I'm very pleased to see it. Thank you.
Thank you.
Richard, the question is very pretty. Is there a similar characterization of S-sorted Cartesian closed varieties?
Many sorted. Interesting. Interesting. I can't answer completely right now, but I think the answer is basically that it always collapses to the single sorted case. So somehow you can always collapse a multi-sorted variety down to a single sorted one by adding enough hyperaffine operations. And I think that means that it doesn't expand the scope any further. So I think you get exactly the same kind of, I think the S-sorted things actually, basically what you end up getting is you get exactly the same data, but you probably have to give a partition of B into S bits. So an S-fold partition of the Bullion algebra B. I think that's the only extra data you get, which sort of picks out your S different sorts. I
think I said something about that in my paper, about the many sorted.
Yes.
And I decided it just wasn't interesting enough to be worth studying separately. So I think it's essentially what you said.
Yeah, I think that's right.
Another question from the chat. Is there potentially a nice extension of Boolean algebras, these operators?
Yeah, I mean, that's a good question. I don't completely understand if there's an intrinsic way of capturing Boolean algebra with operators. I mean, you have these equivalences. You can always sort of stick operators on the Boolean algebra side, and they correspond to nice things on the sort of topological side. But I don't know how to sort of make those sort of appear intrinsically out of nowhere, as it were. So I'm not sure if they fit sort of directly into this picture. But I mean, it'd be interesting to know.
Okay, I think we can stop because we only have 4 minutes to the next talk. But let's thank the speaker again.